Hello, I'm Yishai Oltchik, and this is Brief Announcement, Network Partitioning and Avoidable Contention. You can find the extended version of this paper on Archive. So let's get right into it. Parallel computations are often communication bound, with the bottlenecks manifesting as either busy process or as link contention. In order to mitigate the effects of this link contention, high-performance networks are often designed with an emphasis on the global bisection bandwidth. But there's a small problem with that. So here you can see the activity monitor of a specific supercomputer named Mira. And every concurrent job is color-coded. So this orange rectangle is one specific job that is being executed. And as you can see, it is simply too small to be affected by the global bisection bandwidth of the entire system. In this work, we will show how to decrease contention for all job sizes for certain network topologies. So let's outline our contributions. First, we introduce a novel lower bound for the edge isoperimetric problem for torus graphs, generalizing a result by Bolobash and Leader. Using the above bound, we optimize the processor allocation policies of torus-based systems, and we conduct a case study of BlueJean Q systems, Mira and Uqueen. However, due to time constraints, I will only be able to discuss Mira today. So let's move on to some definitions. So first of all, a torus graph is a Cartesian product of cycle graphs, and if all of the cycles have equal lengths, then we say the torus is cubic. The edge isoperimetric problem is defined as follows. Given a graph G and integer t, what is the minimal size of a cut induced by a subset of exactly t vertices of G? And this is NP-complete, of course. Now, to the hardware side of things, we have processor allocation policies. And these policies are the set of rules that, a large distributed system uses in order to map computations onto the physical hardware. And these policies also constrain the physical geometry of the job. So now let's quickly describe our result for the EAP of torus graphs. And this is, of course, an extremely high-level description. So our result says that in d-dimensional torus graphs, subcuboids that have their r-smallest sides with full length and all of the remaining dimensions are cubic, then these cuboids are isoperimetric for some integer r. You can, of course, find more details in the paper. If you're curious to see the full result, then here it is. However, unfortunately, due to time constraints, we cannot fully discuss them here. You can see everything in the paper. Now let's talk a little about network topology, torus network topologies in practice as they're being used. So we have the Cray XK series, and we have the IBM BlueJean Q series. These are both somewhat old, but we also have the Fujitsu Tofu 2, which is the network used by Fugaku, the current #1 supercomputer in the world. And this is also a high-dimensional torus. Now, when torus dimensions are not greater than 3, then some systems will have a cubic layout and others may not. But for the existing solutions, including BlueJean Q and Tofu 2, it is not possible to have an entirely cubic network in all dimensions. In all dimensions, and this is because some of the dimension sizes in these networks are fixed, and they're also really small. So it's just not possible to have a cube that is sufficiently large to be interesting and useful. Okay, so now let's talk about the BlueJean Q more specifically. The basic allocation unit of a BlueJean Q is a physical construction called a midplane, which is a torus of the dimensions listed here. And these midplanes are interconnected using a 4-dimensional torus. This means that the smallest dimension of the midplane is internal and does not participate in the larger network. Additionally, all partitions of a BlueJean Q system must be cuboids, There are some minor exceptions that do not matter for this talk. And due to the special wiring scheme used in the BlueJean Q systems, all partitions are Tori. So even if we take a long torus and we cut it in half, both of these resulting halves will have their wraparound links and will still be toruses. So now let's talk again more specifically about Mira. As we said, it's a BlueJean Q system. It has 96 midplanes. This is what a midplane looks like. And yeah, okay. So this is the processor allocation policy of Mira. And this is our modification. So you can see that we have, in most cases, a twofold increase. Now, let's put this into a more graphical representation. And this is what it looks like. So on the y-axis, we see the bisection bandwidth of each partition. On the x-axis, we see the size of the partitions. In blue is the current partitions of the network, of the system. And in green are our proposed partitions. So you can see that with the exception of the 24 compute node, the 24 midplane partition, we have a 2x improvement across the board, which we argue is quite nice. However, what we've shown so far is just a theoretical, graph theoretic analysis of the bisection bandwidth. Can we actually attain this improvement in practice? So I will now show a ping-pong evaluation that we ran on Mira. In the paper, we'll also have the same on UQueen. And in the extended version of the paper, we also have additional experiments. So for ping-pong, we adversarially split all of the compute nodes into pairs that are maximally distant. And we executed multiple rounds with massive networks that completely saturated the network. And for the results, we can see that we're able to achieve exactly the predicted improvement for every single partition size. So this is quite nice. Now, in summary, we showed a novel EIP bound for general torus graphs. Using our bound, we improved the performance of Mira, or specifically its processor allocation policy. And all of these changes were done purely in software, incurring zero cost. So now conclusions and open problems. So this was a case study of BlueJean Q torus networks, but our approach is generic and applies to any network that can be represented as a graph, given a solution to its specific EIP. And one open question that remains is Fugaku in the latest top 500 is also a high-dimensional torus, but is its processor allocation policy optimal? Many thanks to Argonne National Lab and to Funktionsnetzwerk Jülich for their support in running the experiments. And once again, the extended version of this talk of this paper is available in Archive. Thank you for your time. I'm happy to take any questions.